Hello friends. So in this lecture we are going to study two topics. First is transformation of a random variable, and second topic will be what happens when a wide sense stationary random process is passed through a linear time invariant filter. So we'll cover these two topics. So let's start from the first topic, which is transformation of a random variable. So we know that if we have a random variable capital X and the PDF of X is known, that is fx of X. Now we are forming a random variable capital Y as a function of X. Now this will also be a random variable and we are supposed to find out the PDF of Y. Let me denote it as fy of Y. So to calculate the PDF we use the formula fy of y equal to modulus of dx by dy into fx of x. Now let us understand this by an example. Let us assume the x is a Gaussian random variable and it has PDF fx of x, and we know that Gaussian PDF is 1 upon 2 pi sigma x square e power minus x minus mu x whole square divided by 2 sigma x square. Now we have to write y as a function of s. I am assuming it as ax plus b, where a and b are constants. Now we have to calculate the PDF of y. So we'll use the formula fy of y equal to fx of x mod of dx by dy. But y was ax plus b, so we'll differentiate it with respect to x, so it will become dy by dx equal to a, and mod dx by mod dy will become 1 by a. Now we'll put all these values. So fyy becomes 1 by a 1 upon under root 2 pi sigma x square e power minus x minus mu x whole square divided by 2 sigma x square. But we have to find out the PDF of fyy, which is a function of y, but here everything is written in terms of x, so we'll use y equal to ax plus b and we'll eliminate x by using relation y minus b by a. So wherever we are seeing x, we'll replace it by y minus b by a. So it will become fy of y equal to 1 by a 1 upon 2 pi sigma x square e power minus y minus b by a minus mu x whole square, and it is divided by 2 sigma x square. Let us rearrange few terms. So fyy becomes 1 upon under root 2 pi a square sigma x square e power minus y minus b minus a mu x whole square divided by a square sigma x square 2. So it can also be written as 1 upon under root 2 pi a square sigma x square e power minus y minus b minus a mu x whole square divided by 2a square sigma x square. Now this also seems as a Gaussian PDF. since the nature is Gaussian, so we can write it as 1 upon under root 2 pi sigma y square e power minus y minus mu y whole square divided by 2 sigma y square. So upon comparing, we get mu y as a mu x plus b and sigma y square equal to a square sigma x square. So from this discussion we can deduce some results. First is, if x is a Gaussian random variable, then y equal to ax plus b will also be a Gaussian random variable. Next point is, if y is equal to ax plus b, then mean of the y can be calculated simply by taking expectation operator, and it will come out as a mu x plus b. Third point, if we have a relation y equal to ax plus b, then the variance of y will be equal to a square sigma x square. The constant term will not have any effect on the variance. So these are very important points. All these points we must remember. Now let us move on to the second topic, which is response of an LTI system for wide sense stationary random process. So first of all, let us understand what is a wide sense stationary random process. Suppose we are considering an x of t as a random process. So this x of t, I'm saying that it is wide sense stationary random process. What does it mean? It means if I'll take mean of this random process, then it will come as mu x, which is a constant value independent of time. So for a wide sense stationary process, the mean should be constant. Now second point is, if I am calculating autocorrelation, that is t1 comma t2, so autocorrelation can be calculated as ex of t1 into x of t2. This autocorrelation function should be the function of the difference of the time instances. So I can write it as, if rxx of t comma t plus tau, then I can write it as expectation of x of t into x of t plus tau. Then the autocorrelation function should not depend on t1 or t2, or here I can say that it should not depend on t1 and t plus tau, rather it should depend on the difference of t plus tau minus t, which is equal to rxx tau. So if any random process satisfies these two conditions, that mean is constant and autocorrelation function is the difference of time instances, then that random process is called as wide sense stationary random process. Now let us pass it with an LTI filter. So this is our wide sense stationary random process x of t. Since we are assuming an LTI filter, so h of t will be there, which is known as unit impulse response of an LTI system, and I am assuming yt is also a random process. So let us have a look what happens with yt. So first of all, here I am saying that x of t is a wide sense stationary random process, which means the mean of this process is constant, which is mu x, and the autocorrelation function, that is I'm assuming t1 and t2, it is equal to ex of t1 into x of t2 is equal to the function of difference of the time instances. Now what about h of t? H of t is unit impulse response of an LTI system, and LTI system will exist physically, so it cannot be a random process, rather it will be a deterministic process. Why this is? Because it is representing an physical LTI system, so it will be some combination of RC filter or some combination of components. So this will always represent a deterministic process. Now since it is an LTI system, so output can be written as h of t convolution with x of t. We are using convolution property because the system is an LTI system. Now y of t can also be further expanded as y of t equal to minus infinity to infinity x of t minus alpha h of alpha d alpha. So we have written the property of the convolution. Now we are interested in calculating the mean of the random process. We will calculate mean and autocorrelation of yt, and if mean comes as constant and autocorrelation comes as the function of difference of different time instances, then we'll say that yt is also a wide sense stationary random process. Till now we are assuming only that yt is a random process. We are further analyze that how this random process can also be said as wide sense stationary random process. So first of all we are calculating the mean. So for calculation of mean we'll use expectation operator, so it will be minus infinity to infinity x of t minus alpha h of alpha d of alpha. Now expectation of yt can be written as minus infinity to infinity. Expectation operator is always operated on a random process, so expectation operator will come on the random process. H of alpha is a deterministic process, so we'll taking it as common. Now expectation of yt can be written as minus infinity to infinity. We already know that x of t is wide sense stationary random process, so its mean will be a constant value mu of x. Even if the time is shifted, then it does not affect the mean, because mean remains the same even if we are using the time shifting operation. So we can write it as mu of x h alpha d alpha. Since mu of x is constant, so it can be taken out from the integration, so it becomes mu of x minus infinity to infinity h of alpha d alpha. Now we know that from the formula of Fourier transform, it is nothing but h alpha e power j omega alpha d alpha. Now if I'll put omega equal to 0, so it becomes minus infinity to infinity h alpha d alpha. So I can write it as expectation operator of y of t equal to mu x h of 0, or I can also write as mean of the random process yt is equal to mu x into h of 0. Since mu x is constant and h of 0 is also constant, then mu of y will also be constant. So we have proved that for random process yt, expectation of yt is a constant value which is equal to mu x into h of 0. Now we'll calculate the autocorrelation function. To calculate the autocorrelation function, we know that ryy t1 comma t2 is equal to expectation operator y of t1 into y of t2. Now we can write y of t1 as minus infinity to infinity x of t1 minus alpha h of alpha d alpha, and yt2 as x of t2 minus beta h of beta into d beta. So we can further rearrange it. We are writing integrations side by side, and it becomes h alpha into h beta x of t1 minus alpha x of t2 minus beta d alpha d beta. We know that h alpha and h beta are deterministic processes, so the expectation operator will be taken only on the random process, which is x. So ryy t1 comma t2 becomes minus infinity to infinity h alpha h beta expectation operator x1 of will be x of t1 minus alpha into x of t2 minus beta d alpha into d beta. Now we know that x of t is wide sense stationary random process, and for this x of t1 into x of t2 is equal to t1 minus t2. So x of t is wide sense stationary random process, so this expectation operator will represent an autocorrelation function, and this autocorrelation function will be the function of the difference of the time instances. So we can write it as r xx t1 minus alpha minus t2 minus beta. Now let me rearrange this. So from here ryy t1 comma t2 becomes minus infinity to infinity h alpha into h beta into rxx of, we can see what is this. So it will be t1 minus t2 plus beta minus alpha. So it will be t1 minus t2 plus beta minus alpha, and it is d alpha d beta. So we can see ryy of tau is a function of difference of the different time instances t1 and t2. So it can also be written as, or we can write it as tau. So it will be minus infinity to infinity h of alpha h of beta rxx of tau plus beta minus alpha d beta. So the autocorrelation function of yt also is coming as the function of the difference of the t1 and t2, so can also be written as r1 of t1 minus t2. So the conclusions for yt came out as the expectation of yt is a constant value which is equal to mu of x h of 0, and also the autocorrelation function of yt came out as the function of the time differences. Since yt is satisfying these properties, so we can say that random process yt is a wide sense stationary random process. So from here we can conclude, if the input of an linear time invariant filter is a wide sense stationary random process, then output will surely be a wide sense stationary random process. And I'm also adding a statement: if x of t is Gaussian random process, we know that a Gaussian random process is a wide sense stationary random process, then y of t will also be a Gaussian random process. So these two results are very important, that if x of t is wide sense stationary random process, then y of t will also be a wide sense stationary random process. And second is, if x of t is a Gaussian random process, then y of t will also be a Gaussian random process. Thank you.